In this video, first we will understand what is critical angle, and from this we will understand the total internal reflection phenomena. So what I have kept here is a water, and then outside here is all air. So my medium one, from where the incident ray will come, that is optically denser. Water is denser than air, and the medium two is our air, which is, we can say, optically rarer. We are just comparing water and air here. Now, when the light goes from a denser medium to rarer medium, what will happen? It will go away from the normal. The angle will increase. The sine theta value will increase. Let me take an example. So inside this water, I have a laser light and I shine it like this. I have already drawn a normal beforehand at this point of incidence, so I will shine my laser light at this point. So let's say I have shine my light like this. There will be some angle. This is my angle of incidence, theta 1. And now what will happen? Light will not go straight because it is changing medium. It will speed up in this case and it will go away from the normal, right? So let's say it bends like that. It's exaggerated, but let's say it is this angle. So now if you see, the angle has increased, right? So let's play around and I will now increase this incident angle. I will shine the laser light from somewhere here. Let's see what happens to this light ray. Now I will shine it like this. I'm increasing the angle of incidence. So this will mean I'm angle of incidence. And now if you can observe, light is bending away from the normal. That is right. But this reflected ray, if you can see, it is coming closer to the interface. And that is the main thing. Now I will go play around more. What will happen if I increase this angle? So it will bend more towards this interface. And gradually, if I increase this angle, I'll be able to observe, let's say, this angle. I will incident light on at this point. This is my incident angle, and now light has to bend away from the normal, but the incident angle is huge. So what is happening? The light, instead of, in the last case it was going somewhere here, in this case it will just go on grazing the surface. It will skim along the interface. So this point is critical, and this angle is also we call critical angle. What is happening if you want to note down the angle of refraction here? That is 90 degree. So that is one condition for this critical angle. It is the angle. If we go on increasing the angle of incidence, here coming from denser to rarer, a angle will come in which the refracted ray will start going along, traveling along the interface, or we can say the angle of reflection will become 90 degree. Same thing. This is called the critical angle. This is the condition for critical angle. Critical angle. And now the fun begins. What if we increase more than that? If I shine the light from somewhere here, what will happen? Let's see. So if I'm making angle more than critical angle, the angle of incidence is more than critical angle. Here the condition is the angle of incidence is greater than critical angle. It's greater than critical angle. Then at critical angle, it was skimming through the surface. Now what will happen? It will start reflecting back into the denser medium. So what we are having, if we are keeping this condition, if we are going beyond the critical angle, we are finding there is no refraction. No refraction. Yeah. And what is happening instead? The light is bouncing back into the same medium, or we are getting reflection. Yeah. And this phenomena, that instead of refraction, if we go beyond critical angle, what will happen? There will be no reflection, but the light will bounce back and it will start reflecting within a medium internally. We will call this phenomena total internal reflection. To understand better, we can have a simulation. So here's a laser light, here is water, and below and shown in white is our air. So the light will go, if I shine a laser, it will go from denser medium to rarer medium. And when that happens, the light will refract away from the normal, right? And if you see this part, this is a little bit of reflection, which will always be there. When we talk about generally about refraction, we just ignore this part, but it will be always there. This surface, this interface will also work as shiny mirror. So some part of light will always reflect it back into the denser medium already, but not the whole, not the total one. But now what will happen if I go increasing, see, it will approach the interface, and some point it'll go on grazing the surface or skim along the interface. And after that, if I just increase this angle, let's say this is the angle, after that it'll just go internally, it'll bounce back internally, it'll reflect. There is no refraction here, right? That case is over, right? And this angle we call critical angle, and approximate we can take this angle as the critical angle, and we can measure this also. So we will take this and we will put it here. So because we are taking angles always from a normal, so I will start my zero here, so 30 degree, and it is 40 degrees, so just a little bit lesser than 50 degree. I think 49, 48, around that. So let's say we are assuming like the critical angle is 50 degree. Now what will happen after that? You do anything, you've increased this, light will, we can restrict light into the same medium internally. And also we can word use, this is the total internal reflection. There is no light passing through in part of reflection. It is totally reflected back. There is no part of this light beam which is going into the other medium. So we saw in our simulation that water to air, if we are incidentally light, the critical angle is coming approximately equal to 50 degrees. We measured that in simulation, but we can calculate that also, and we can use a Snell's law to calculate the critical angle for different mediums. And we will see where, what comes the value for water to air. What is the incident angle? What is the critical angle where the refracting angle becomes 90 degree? If we know this condition, we should be able to calculate that. So let's see what Snell's law says. Let's say N1. This is the first medium which is denser, and we are shining light, say, at this angle sine theta 1, then it has to be equal, right? The product should be equal to n2 into sine theta 2. Now, what is the condition of angle of critical is the angle of refraction becomes 90 degrees. So let's apply that. So let's say we know n1 and sine theta 1 we want to calculate. So this angle of incidence becomes critical, right? Theta c. So I'm just putting a subscript here c for critical. So if this is the condition, what will happen to the other side? The sine theta 2, the angle of refraction becomes sine 90 degree. Then only we will say that it is a critical angle, right? That angle of incidence where the angle of refraction becomes 90 degrees. So we have just applied what we have learned in the Snell's law. Now, the good news is sine 90 value is 1, right? Sine 0, 0 and sine 90 is 1. So we can ignore this part completely. And now what we are seeing, we want to calculate this. As we were doing in different questions, we will do theta sine theta c, that will be equal to n2 divided by n1. And if I want to calculate this in degrees, so I will take inverse both sides. I will say critical angle will be sine inverse of n2 divided by n1. Remember, this second medium is rarer, and this is denser. So I'm just mentioning that so that we are not confused with the formula. So we need to remember this formula. Take a note of this question, this formula. Remember this formula, and you'll be able to calculate the critical angle. Now let's come and calculate. Let's discuss how we can calculate for water to air. So we know for water, the water is the first medium, so n1 is 1.33, and for air, that is our n2 refractive index will be air. We can take as 1. So now we just need to plug these values here. So the critical angle for this scenario will be, we have to take sine inverse. So we just need to take inverse of n2 by n1, or 1 in our case, 2 and 1, 1.33. So let me use my calculator here. So here is my calculator. I will take this 1 divided by 1.33. So that is my n2 by n1. And I will take sine inverse of that. And I will get 48.7 degrees. So that is my critical angle for the condition which we have given, that the medium is water to air, denser to rarer. So that's how we can calculate this. And if you see on simulation also, we were getting around 50 degree. And here what we are getting is around 50 degree only, 48.7. So that's what our hunch under simulation was correct. So this is the way we can calculate the critical angle if two mediums are known to us, that their refractive index is known to us. So what we will do, we will calculate the ratio, rarer to denser. Remember, rarer to denser, and 2 by n1, and take a sine inverse of that. Whatever angle that comes, that is the critical angle for those two mediums.